this is the GUI of Turbo Design 1, which we'll use to design the blades for the impeller, diffuser and the return channel vane. So starting with the impeller first, we can first import the file that was exported from the mainline code Turbo Design Pre. So we can open the impeller file first. And we can see immediately the different sections are populated with information from Turbo Design Pre. So if we start with the specifications first, the machine type, the material and the duty point details, they all come directly from the mainline code. Then the next section is meridional design, and if we check the plot first, we can see that this meridional shape automatically came from the mainline code, and we can also see this two-dimensional grid has been generated automatically. And note here that even though the grid is 2D, the solver is still 3D because it's solving in the third dimension using Fourier series. And so even though the solution is fully 3D, it's still very fast because it's working on this two-dimensional grid. Now if we open the meridional editor, then we can see that the meridional geometry has been automatically parameterized since we selected the parametric MRI export option in Turbo Design Pre. And so all these different geometric parameters can be easily included in a multi-point, multi-objective optimization later on. Now the next section is thickness. And we can see we have different options to specify the thickness. So we have the normal option as well as the tangential option, and for the distribution we again have several different selections such as constant, NACA or control points, and by default we have this constant distribution, but in this case we can also import an external thickness profile using this option here. And then if we select the impeller profile, and now the solver is using this profile imposed by us. Now the next section is blockage, and we only use this for cases with significant boundary layer blockage, so we can skip this for now. The next section is blade loading, and this is very important when as far as inverse design is concerned, and this consists of components. So the first thing is the span-wise work distribution, and here we can see that it's 0 from hub to shroud at the leading edge because the flow is assumed to be fully axial coming into the impeller, whereas at the trailing edge it has a finite value from hub to shroud. But this is a free vortex distribution since it's a constant value from hub to shroud. But of course in 3D inverse design, the advantage is that we can also use a forced vortex distribution by changing the variation from the hub to shroud, and this will give you a fully 3D design. The next component of blade loading is the streamwise distribution, and here we actually specify how the loading changes from the leading edge to the trailing edge at different span-wise sections such as hub and shroud. And finally, the next section is stacking, and what this means is the wrap or lean of the blade in or against the direction of rotation. And we can start with 0 stacking at the trailing edge, which is the streamwise location of 1, and do make sure to select the linear option here even though you have 0 stacking at both the hub and shroud, because this will enable the stacking to be included as an input parameter for optimization later on. And with all the different options specified, we can generate the design of the impeller now by clicking the Run button here. And just like that, within 5 seconds or so, we have the impeller design with us. And we can actually visualize it using a 3D plot under the post-processing section. And we can then activate all the blades. So now we can clearly see the 3D shape of our impeller. And we can see that case 1 has appeared in the project manager window, and if we open the performance parameters, then we can see that we have quite a few different output parameters based on this envisaged solution. And for example, an indicator of secondary flows or diffusion ratio, which is an indicator of flow separation, profile loss, leakage loss, and also some geometric parameters such as throat and maximum lean. And so what we can do is we can select some parameters of interest. Just like this. And then we can actually choose to see only the selected parameters. And we can rename this to impeller. And under post-processing, we also have other options such as 2D plots of any variable of choice, such as the static pressure at different span-wise locations. With the impeller design ready, we can move to the next component, which is the diffuser. And the way we can do it is we can now import the diffuser file that was exported from the mainline code. And now we can see all the options have been pre-filled for the diffuser this time. So the machine type, the blade row has changed to diffuser, and the inlet conditions have been updated accordingly as per the mainline results. So the next section is meridional design, and again we can see we have the meridional shape of the diffuser along with the two-dimensional grid. And for the thickness, we have a NACA profile by default, but we can also import an external profile. So the diffuser profile. And then we can again skip blockage in this case. And if we go to blade loading, then we can see that we have again the span-wise work distribution first, and this time we can see that the leading edge value is actually quite close to the trailing edge value of the impeller, and this automatically ensures a good matching between the two components. And for the stream-wise blade loading, we can see that the default loading that came from the mainline code is a generally 4-loaded distribution for the diffuser. Stacking can be left to 0 in this case, and then we are ready to generate the diffuser design by clicking run. And again, very quickly we have the diffuser design with us, which we can actually visualize with a 3D plot again. So let's activate all the blades. And we have an idea of our diffuser now. And we can see that a second case has appeared in the project manager window, which we can name as diffuser. And now all the different parameters are now available for the diffuser as well. And then finally, let's move on to the return channel vane. And the workflow is exactly the same. The file from the mainline code, this time for the return channel. The specifications are now updated for the return channel vane and the meridional shape as well. So we can see the grid has now moved over the return channel vane. And next comes the thickness. It's a constant thickness, but we can impose a profile again. Something like that. We can skip blockage again, and for the blade load, we look at the span-wise work first, then we can again see that the leading edge loading is now similar to the trailing edge loading of the diffuser, and now this will again ensure a good matching between these two components. And the trailing edge loading is now close to 0 because we want to eliminate software from the incoming flow. And then for the stream-wise loading, again we have a generally 4 loaded distribution in this case. And then moving on to stacking, we can again go with 0 stacking in this case, and then we are ready to generate channel design. And very quickly we have the 3D geometry of the vane, and let's have a look at the vane in our 3D view. Activate all the blades. And these are the return channel vanes. And this has also appeared in the project manager window, which we can then rename as return channel, as well as all the different parameters are available. One thing we can do in the 3D plot is we can compare all the 3 geometries and see their relative locations. So we select all of them in the project manager window, select the combine plots option, make all the blades visible, and now we can see the impeller, diffuser and return channel vanes all at their respective axial locations. And we can also make use of the 2D plots. And if we do a comparison of the static pressure, for example, at the different span-wise locations, so here we can see a comparison for the impeller, the diffuser and the return channel vanes on the same plot. And finally, we can also see some plots in the project manager window by opening the 2D plot from here. And here we can actually do a comparison of a particular performance parameter for the different components. For example, if we select profile loss, then we can clearly see the profile loss of the impeller, the diffuser and the return channel vane and their relative values, and clearly the profile loss of the impeller is the highest among the three. We also have different export options here. For the blade, we can select an elliptic leading edge, for example, to give it a proper rounding. And then for the export domain type, we can either export the blade, or we can select a CFD export or an FEA export as well. And finally, we can export, for example, turbo grid curves for CFD or step files for FEA analysis. And with all the components of the centrifugal compressor stage now ready, they can all now be exported for a CFD analysis of the baseline design.